Hi there, folks. In this video, we're going to be talking about what is the potential energy associated with a compressed or stretched spring. So first, let me just remind you of the basic spring terminology. A spring can be either compressed, in which case it's in compression and it pushes back, or it can be stretched out in tension, in which case it pulls back. And the length here, which I like to mark as a dashed line in my diagrams, where it is neither stretched nor compressed, that's referred to as the rest length of the spring. So if we use the normal reference point for potential energy, which we always will, when the spring is neither stretched nor compressed, it'll have a potential energy equal to 0, which is pretty obvious. If the spring is not stretched or compressed, it doesn't store any energy. On the other hand, if the spring is stretched by an amount x, or it is compressed by an amount x, the amount of energy stored in the spring is exactly the same for the same value of x. It's half kx squared. And down here also half kx squared. You will notice that whether it is stretched or compressed doesn't matter. The potential energy is positive either way. An easy way to remember that is like with the kinetic energy, x is squared there. So it doesn't matter if x is positive or negative. The energy that it gives is the same either way. And that makes sense because if you compress the spring, it has the potential to bounce back. And if you stretch the spring, it also has the potential to bounce back. So in either case, it is storing energy. And remember, energy is not a vector, so there's no direction associated with it. So that's the final punchline, really. And pretty much all there is to say about the spring potential energy is that the formula for it is 1/2 kx squared. And of course, k is the spring constant, the same as it was when we studied the spring force. So 1/2 kx squared. A few additional conceptual comments about the spring potential energy. I talked in a previous video about how you can learn a lot about a potential energy by graphing it. So if we sketch out the spring potential energy, U versus X, it is, of course, a parabola, which I don't know how good I am at drawing parabolas, but we'll try. Okay. So, well, it's a little off-center parabola. But anyways, it's something like that, where it's curved upwards like that. And the minimum occurs at x equals 0 and u equals 0, where the spring is neither stretched nor compressed, and also it's not storing any energy. If you put in a positive x or a negative x, the potential energy is positive. And one thing this tells you, if you think about the idea of potential energy graphs that I talked about before, if you release an object from rest with a stretched spring, it will tend to roll back towards x equals 0. And if you release an object from rest with a compressed spring, it will also try to bounce back towards x equals 0, because on potential energy graphs, objects want to roll downhill. So you'll notice here that rolling downhill on the potential energy surface always means that you're going back towards x equals 0, which makes sense because of the spring force. Remember, downhill on the potential energy graph is also the direction of the force. So when it came to the spring force, we said that the force always pulls it back towards x equals 0. On the potential energy graph, downhill on the potential energy graph always points back towards x equals 0, which is the same statement. And one other thing that is super interesting, but we don't have a lot of time to dwell on it in this class, you'll notice that if an object gets released with a certain amount of total energy on this graph here, so let's say it gets released from rest at this location I marked here, what's going to happen is the object will roll back down towards x equals 0. It'll overshoot x equals 0. It'll roll up the other side of the potential energy surface until it reaches the same level, and then it will go roll back down again. And so it will roll back and forth around the minimum of the potential energy. And this is in the real life equivalent. This is when if you like pluck a spring, what's going to happen to it is it'll bounce back and forth like this. It'll oscillate back and forth. So that's what this behavior represents in the potential energy surface, is the thing rolling back and forth around the minimum of the potential energy. So this is pretty much all you need to know about the spring potential energy. The next step is just to try some example problems where you're actually using the spring potential energy as one or all of the different types of potential energy. Remember, by the way, that if you have more than one type of potential energy, so if you have, for instance, spring potential energy and gravitational potential energy, you'll add them together to get the total potential energy. So this is one of the possible potentials you might have to calculate.